said. So as a revision, the oxyacids are the acids in which a proton is attached to an oxygen. If you have sulfuric acid and the sulfuric acid has S and has O, and the H that will be lost is connected to the oxygen, then it's called an oxyacid. It can happen in the strong and in the weak. So the phosphoric acid is a weak acid. It has an O attached to the H. So the H that's lost is attached to a proton. Also in the organic acid, any acid that has COOH has the H that will be lost attached to O. So it can be a strong, a weak acid. The concentration of H plus and OH minus can be found at 25 degrees from the law that tells you that the dissociation constant of water is equal to H plus concentration multiplied by OH minus concentration, which is equal to 1 multiplied 10 to the power of negative 14. So every one of them is equal. This is water, so it's neutral. So both of them is equal. The concentration of the H plus is equal to the concentration of OH minus, both of them 1 multiplied 10 to the power of negative 7. From which you can easily find the pH of the solution. If you have one of them, you can get the other one. Then you can find the pH. pH is equal to negative log 10 the H plus concentration, and pOH is equal to negative log 10 the OH minus concentration. The pH plus the pOH is equal to 14 if you added them, and this is very useful if you try to find one from the other. If you have pH is equal to 2.5, you can find the pH 14 minus 2.5 directly. How can we calculate the pH of strong acid? That's very easy, because the strong acid completely ionizes into H plus and Cl minus. So 2 molar concentrations give you 2 molar of H plus ions. So you can find the pH by getting the negative log of this one. You can do the same for the base, by the way. But the weak acid, I have a problem. I don't know how much is dissociated. So how much H plus and CH3CO minus is found compared to the concentration of the acid itself, I will only know that by the acid dissociation constant. This tells you the same way K equilibrium tells you how much the equilibrium moves to the right or to the left. Also, the Ka tells you how much the equilibrium moves to the right or to the left. Anyway, for the weak acid, I do know that it's weak, so it mainly goes to the left side. The two reactions happen. Don't forget ever, there is no direction which is only moving and another one is stopping. Since this is equilibrium, always the acid will start to decompose into the constituents, and the constituents will start to join to form the base. It's only that the concentration of this one is higher than the concentration of the products. That's why the numerical value of the multiplication of the product's concentration is much less than that of the reactants. That's why the Ka is weak. That's why the value is small, because the numerator is much less than the denominator. This doesn't happen in the strong acids. In the strong acids, the numerator is much higher. Why? It's even 100% decomposition. So there is a lot of the products and there is no reactants in the strong acids. That's why the Ka is high. The opposite happens in the weak acids. The Ka is very small, so it's weak. Here the number is high, and here it's weak, so the number is low. The number is very low. The same happens in the base. So the Kp is the product of the dissociation constant of the products of the reactants. So if we have NH3, how do you make the reaction for the dissociation? You have to always add water. So don't forget that you need water in the acids and bases. So this forms what? This one loses a proton, and this one gains a proton. So this one loses a proton. No, this is a base. It gains a proton. So it forms NH4 plus and OH minus. Mister, what happens? This is a weak base, so the decomposition is very weak. So the reaction mainly goes to the backward direction, not the forward direction. So Kp is equal to the concentration of NH4 plus multiplied by OH minus, which is very weak, divided by NH3. Should I say here liquid and put it? No, you don't put the liquids. This is still aqueous because it is dissolved in water, and this is aqueous and this is aqueous. Don't mention water in such action. So the weak acid has a very small Kp because this concentration of the product is very small compared to the base itself. It's very weak. What in the strong bases like NaOH, most or all of the base is decomposed into Na and OH minus. That's why the OH minus concentration is very high. That's why the pH is very high. Mister, this one is completely decomposed, so this one is much more than this one, so the Kp is still high. So the calculation of pH and pOH of weak base and strong base follow the same rules. The only way to find it for the weak base is to have the Kp. If you don't have the Kp, there is no chance of knowing how much concentration of the ions is formed. And also in the acids, there is no chance of knowing what is the H plus concentration if you don't have the Ka. But in the case of the Kp, the whole base decomposes. So you know that if you have 0.1 molar of NaOH, you have 0.1 molar of OH minus. And if you have OH minus, you can find whatever you want. You can find the pOH, you can find the pH, you can find the H plus, or you can keep shifting between these three. So again, if you have a mixture of strong acid and weak acid, if you want to calculate the pH, you will make what? You will ignore the H plus concentration that came from the weak acid. Why? Because it's a very small number. You can find it by the ice table and find the H plus and use it with this H plus. But this one must be ignored. That one must be ignored. It's very small number compared to H plus. We resembled it to the example of somebody giving you a lot of money. So he gave you $1 million, and then somebody else has given you $1. So if I asked you how much money you do have, you will not say I have 1,000,001. You will say I have 1 million. So you ignore this one because you have very high concentration from here. So when you are trying to calculate the pH, you will use it from the strong acid or the weak acid. You will use pH equal to negative log 10, that's 0.1. What about that one, mister? Why did you put that one? Because that number is very small compared to that number. If you even find it, you will see that the pH is not affected much by that one. So like that, if you see the pH is, for example, calculated for 0.1, what is 0.1 pH? I'll make negative log 0.1. So in the calculator 0.1, the negative log of this value will be, I will say, negative log 0.1. So it came as 1. So the pH is 1. If you found how much pH will be moved or changed by this HF, you will see that it's almost non-moved. That's why I will ignore it. If you need to find the pH of a mixture of weak acids, you have to focus on what? You have to focus on what are the major species that you have, because this is what will guide you. I have a mixture of HCN and HNO2. The first one concentration is 1 molar. The second one is 5 molar. And you also need to find the pH and the concentration of the CN minus. This is part B of the question. The first thing to find the major species. The species which are not decomposed are water. HCN, HNO2. There is still CN minus, but very small. OH minus very small, NO2 minus very small, because the Kas are very weak. Nevertheless, if you are wanting to find the pH, you have to find the major source of the H plus, which of course is the H plus that came from the highest Ka. Since HNO2 has the highest Ka, so the H plus coming from it will be the highest concentration of H plus. That's why I will make the ice table using the HNO2. The HNO2 will give me 5, gives 0 to 0. This is the initial concentration of HNO2 that I gave you. Minus X plus X plus X. Continue the ice table and get the X. Once you find the X, get its radical. Once you find its radical, don't forget that the X that you found is the H plus. Then you can find its minus log to find its pH. So the pH came from the H plus that came from the HNO2, and you have ignored the H plus that came from the water and the HCN. Why? Because it's very low concentration. The next part in the question, you're trying to find HCN. So also you will make the ice table. The ice table gives you H plus and Cn minus. So Mr. H plus and Cn minus, when it breaks down, you have 1 molar of HCN. Mr. H plus and Cn minus, the Cn minus, I don't know its concentration, but what is the H plus? This is the H plus that came from the HCN. But this value is useless. You should ignore it completely and go back and find the H plus that came from HNO2. Why? Because this is like the million that's added to a $1. You ignore the one and you count the million. How much money when you have when you add the million to one? You have $1 million. You can still say 1,000,001. The number of zeros here, by the way, is very much wrong. It's 1, 2, 3, 4, 5, 6. If you are saying million, but the idea is that you ignore the small number and you say, I have 4.510 minus 2. This is the H plus that came from the HNO2, which is very big compared to the one that comes from HCN. So I will ignore that one and I will use this one alone. Start bragging in the numbers. The HCN is the one. Then you can find Cn minus by dividing this value by H plus and Cn minus. So you get the Cn minus concentration 1.4 multiplied 10 to the power of -8. That's how you find the pH of a mixture of weak acid. Here, the acid dissociation constant, or the base dissociation constant gives you an idea if it is weak acid or weak strong acid or weak base or strong base, but not a clear idea. The percent dissociation gives you a very clear idea. For example, it's 2%, 5%, 10%. How do you get the percentage dissociation? It's equal to the amount that is dissociated. How do you measure that? In mole per liter, divided by the initial concentration. The initial concentration multiplied by 100%. Again, the concentration in mole per liter. So, for example, in the example before, we found that the acid, which is dilute, for example, was 1 molar, for example, of HF, and H plus is equal to 2.7 per 10 to the power of -2. That's the H plus concentration that we get, for example, from another example. So the initial concentration was 1 molar. You had the acid before dissociation was 1. And how much is dissociated? The concentration that's dissociated is only 2.7 per 10 to the power of -2. The rest is the same. If you multiply this by 100, you will get 2.7. So this gives you a very good idea how much is the amount of the acid that is broken down. Only 2.7 out of the total amount is broken down. Again, this gives you a good idea. The acid dissociation constant just told you that it is weak acid. Weak to which extent, you don't know. You know it only by the percentage dissociation. You can do the same with the base exactly. How much is dissociated compared to the initial concentration. Right. Let's see another example, or a fast example to how to do that, since we have a little bit more time. It's often useful to specify the amount exactly. ازاي يا مستر؟ يعني calculate percent dissociation مثلا لأcetic acid. Its Ka is equal to 1.8 multiplied 10 to the power of -5. The first solution that I want to check is 1 molar of the acid. Mister, you have to find first the H plus. How do you do that? By the ice table. So I will not make the steps. You find the ice table, you find the H plus. Then how do you get the percentage dissociation? You divide the H plus concentration, which you will get. Let's say that we found out, just for the sake of time, we found it is equal to what? I will say 4.2 multiplied 10 to the power of -3. And what is the initial? It was 1. So when you divide this by 1, it's just by chance 1, like the previous example, and you multiply it by 100, you get 0.42. So this is even weaker acid. Even weaker acid compared to the other acid. The percentage dissociation is very weak. Okay, still we have one more last idea, is the relationship between Ka and the percentage dissociation. So I found out that the calculation of this one has a different way than that one. This one, we get the Ka is equal to products divided by reactants concentration to the power of their coefficient, while this one is equal to the final concentration of the acid divided by its initial concentration. So the amount that's dissociated divided by the initial multiplied by 100. So the dissociated divided by the initial multiplied by 100. But is there any relationship between both of them? Like there is a way that I can find one from the other better than going through the details? Because if I don't have a relationship, all I can do is find the H plus and then take the H plus and divide it by the initial and then find the percentage dissociation. Or if I have the percentage and I want to do the opposite, I can find the initial and then use it with the K to find the Ka, and then it's an indirect way. Now let's have an example to find that. I have, for example, lactic acid. If we take biology, we know that this lactic acid is what's produced in the muscles when you are fatigued or tired. So let's say that I have a solution of 0.100 molar aqueous solution of lactic acid. And I have its percentage dissociation equal to 3.7 out of what's totally dissociated. And I need to find the Ka. Mister, I know that the Ka is equal to H plus. So if the acid formula is H, we'll just simplify it as HC3, H5O3. I will say that Ka is equal to H plus, and what's remaining here after removing the H, to C3, H5O3 minus, divided by the acid concentration. So again, I can find the ice table and I can find the concentration. Actually, I think it will be better if I give the formula in the next time. I think it's just because I'm trying to stress too many things in the same lesson. So just see it in the next lesson.